Okay, I hope this is going to record okay. Hello, and welcome to a series of lecture videos over the foundations of mathematics. These videos will cover a number of subject areas in the realm of mathematics, including but not limited to college algebra, calculus, some set theory, logic, and things of that. Things related to those fields. So anyway, in this first lecture, we're actually going to cover the very basics of mathematics, and I'm referring to things such as set theory, logic, some of the field axioms of the real numbers, and expansions and factorizations of polynomials. So, to begin with, and I hope this shows up okay on the video feed here, we're actually going to cover, my marker will do it correctly, we're actually going to cover, first of all, sets of numbers, okay? And there are a few sets in mathematics that are really very important to us, as these help to really kind of establish the framework within which we work in mathematics. Alright? So, the first thing you want to note is that the null set is given as the set containing no elements, or by this little symbol, it's like a 0 with a slash through it, right? That really is one of the key sets. It's the empty set or the null set in mathematics, and although the idea may seem to be a little counterintuitive, it really doesn't have anything in it. Absolutely nothing, not even 0 is in that set. And I know a lot of people seem to kind of struggle with the idea of there being an empty set, but it does actually exist. So the second set that we want to consider is the set of natural numbers, okay? So the set of natural numbers is given by this n, boldface n, and that's defined simply as your positive counting numbers. Okay? Now this set is infinite, and that's one of actually the axioms of set theory, which is slightly controversial in modern day mathematics. Some people ask, well, how do you know that this set is infinite? How do you know that it goes on forever? But we're going to take that as an axiom. And an axiom is a type of assumed truth. We're simply going to assume it to be true without my giving you any kind of formal proof that it is actually indeed infinite. So anyway, and this is one of the most fundamental sets of all of mathematics, okay? However, note that 0 is not actually contained in this set. If we were to add 0 to this set, we would have the set of whole numbers. This set is given to us by W, boldface W, which is defined as the set containing 0 union natural numbers. This symbol right here is read union, okay? And this is saying that, here's a little background for set theory, right? If you're given two sets, given A and B, A union B is defined as the set X such that X is in A or X is in B. Okay, this little vertical bar right here is read such that this is read is in or is an element of. Okay, so if you're given these two sets, A and B, and a set really is any collection of objects, right? If you're given these two sets of objects, or these two sets, then A union B is simply saying that X can be in A or X can be in B. But because we're using the mathematical sense of or, this could also mean that X is in A and B. I know it seems a little weird, but in mathematics, to say that something or something is true means that one thing could be true or the other thing could be true, or they could both be true at the same time. So it may seem a little weird, but that's the way we define or in mathematics. So that's the set of whole numbers, right? Now the set of integers is another really important set. So the set of integers is given as z, boldface z, and this is defined as the set W union, so the whole numbers, union with the set negative n, such that n is from the natural numbers. Okay? And this could also be said to be equal to the set given here, okay? So this is simply your positive counting numbers, 1 through infinity, and again this set is also infinite, 0, and then the negative counting numbers, -1, -2, and so on and so forth. So that's the set of integers. Again, this is a very key set in mathematics, and it's also infinite. However, its size is actually greater than the size of the natural numbers because it actually includes 0 and the negatives as well. So that's a little concept that we'll get to later when it comes to differing types of infinity. So another set that we're going to consider is the set of rational numbers. This is denoted by a boldface Q, and this is the set M over N such that M and N are in the set Z, and N is not equal to 0. Okay? So most of you are probably familiar with this set intuitively anyway. This is simply the set of your fractions, but note that this can also have integers in it, as the elements in the set are from the set Z, right? So 1 is actually a member of this set because 1 over 1 is 1, or any number over itself is 1. And that's another important property of the real numbers that we'll examine later. So that's the set of rational numbers. Another set, you can kind of think of this as the opposite of this set, the set of irrational numbers is given as H, boldface H. Some people choose H as the letter to represent the irrational numbers, and others will note that this is actually used to denote something different in mathematics, and that's actually something, notation is a problem that we run into a lot in mathematics. You'll find that a lot of notation is used in several different ways to mean different things, but generally the context will make it clear as to what that symbol is supposed to be. So anyway, with that said, I'm using H here to denote the set of irrational numbers. And this is also defined as, more specifically, the set of real numbers minus the set Q. And this is actually a set difference. This is actually equal to, rather, the set X, such that X is in R, the real numbers, which we'll get to shortly, and X is not in the rationals. Okay, so this is the set of all of the real numbers, right, that are not rational, okay? So, for example, things like the square root of 2, pi, e, these are all in the set H, okay? Because these can simply not be written as rational numbers or ratios, okay? Item number 7, this is really one of our key sets, okay? The set of real numbers is given as R, boldface R, and this is defined as the set Q union the set H. So the rationals union together with the irrationals, okay? And this is really the universe, or rather the universal set in which we usually work. But there is one other set that you want to keep in mind. This is something in abstract algebra we refer to as an extension field. The set of complex numbers is given as boldface C. This is defined as the set A plus BI, such that A and B are actually from the set R. Okay? And then I is the imaginary number. I here is the square root of -1, because if you notice in the real numbers we cannot actually take the square root, or more generally a positive even root of negative numbers. Okay? So, with that being said, with our sets of numbers given, let's go over some of the field axioms of the real numbers, okay? Now, they're referred to as field axioms because, again, well, they're actually assumed truths, right? They actually come from the fact that R itself is actually something referred to as a field in abstract algebra. And a field has with it certain properties that are actually just part of the definition of being a field. So for A, B, and C in the real numbers, the following hold. Okay? So, number 1, A is equal to itself, alright? This is a really important property. This is referred to as the reflexive property. And this simply says that if you have a number, it's actually equal to itself. Similarly, if A equals B, then B must equal A as well. This is the symmetric property of real numbers, okay? And then finally, this last one, which is also related, if A equals B and B equals C, then A must equal C as well, okay? And this is something referred to as the transitive property. Now, if you've had a little background from a course in mathematical reasoning, then you'll actually recognize that these past three statements are actually part of what we refer to as an equivalence relation of numbers. But that's something that we'll get to later, since right now we're just really kind of dealing with some very basic ideas, okay? So, property number 4. A plus B is equal to B plus A. Simple enough, right? This is actually, again, it follows from the field properties of the real numbers. This is the commutative property of addition. And again, this follows from the fact that R is a field, and actually in abstract algebra you'll learn that in order to be a field, you have to be what's referred to as an abelian group under addition. But again, that's something we'll get to later. Property 5 is A times B is equal to B times A. This is the commutative property of multiplication. Okay? So it's similar to addition, but instead of addition as our operation, we have multiplication. Okay? Property 6 is A plus B plus C is equal to A plus B plus C. This is the associative property of addition. And I'm just going to use a plus sign to denote addition to conserve space and to save time. Likewise, A times B times C is equal to A times B times C. And this is the associative property of multiplication. And here I'm going to use the dot to denote multiplication. Property 8, this is actually a very key property. So there exists an element 0 in the set of real numbers such that A plus 0 is equal to A is equal to 0 plus A. Okay? This is the additive identity. Okay? This is saying that if you add 0 to a real number, then the result will actually be that real number. Okay? Likewise, there exists an element 1 in the set of real numbers such that A times 1 is equal to A, which is equal to 1 times A. And this is the multiplicative identity. Property number 10. For each A in the real numbers, there exists an element negative A in the real numbers such that A plus negative A is equal to 0, which is also equal to negative A plus A. Okay? This is referred to as the additive inverse. Okay? The idea of inverses in mathematics is really key to a lot of mathematics, because for any operation, the inverse of an operation basically undoes what the first operation did. So if I add two numbers, well, then subtracting them would be the inverse of that operation, okay? And here subtraction is indicated by adding a negative to a number.